My name is Benjamin Peters. I'm one of the conference organizers here. In particular, I had the pleasure of organizing the GACs here. Before we start into the first GAC, I'd like to talk a bit about the GAC program. So the generative adversarial collaborations are one of these examples that Talia mentioned as a community contributed program item and has been very successful and very unique to CCN. So GACs, we now call it like a new model of scientific discourse. The idea is that science advances through the exchange between alternative ideas and theories. But often we have these theoretical silos, so people don't talk to each other in different theoretical camps, and a lack of common understanding, and that often impedes these kind of productive exchanges. And so this is where GACs come in. So what is it? So we'll see it live today. So researchers with alternative theories collaborate to resolve their differences. They come together to develop a shared common language and possibly to design the best way to adjudicate among theories. And so here the common language is actually what Matthias just called a shared reality, so constructing a shared reality between different theoretical camps. And so why? Of course, to accelerate scientific progress. So if you want to read more about this, we just recently put out a preprint on the GACs in CCN and the experience. You can also go to gac.ccneuro.org and browse this and see what we all have done already. So since 4 years, we have 15 GACs. There's now 8 papers on these GACs, and you can read them. There's, for each of the GAC workshops, there's a recording you can watch, and that's a very valuable resource. So this year, we have 2 GACs. One is here, is V1, a cognitive map. And on Thursday, we have Attending to Errors in Predictive Coding, a collaborative community experiment through the Open Scope program. In addition, we have poster updates, so that's also part of the GAC, that a year or 2 years later, you come to CCN and present the update on your GAC. And we have 2 posters, but with a caveat that I just learned the second poster cannot take place because the author that wanted to present it couldn't make it in time to the conference. But please go to the other poster, A159, right after this GAC. Okay, without further ado, let's welcome our GAC and panel members.
Great. So thanks so much, Benjamin, and thanks to everyone for coming today. So as you'll see, the title of our GAC is V1 a Cognitive Map? And the question of this GAC is essentially, what is V1, the primary visual cortex, doing? And traditionally, there's been 2 very different approaches. So one has emphasized the feed-forward dimension of V1, right? And this has been the approach that's dominated from the 1960s to the 1990s and through to the present. So the emphasis is on V1 sending signals to further visual areas in the ventral and the dorsal streams. Under this account, V1 is sort of typically seen as a preliminary processing stage, right? So the idea is that V1 may do some processing. It might do some image processing, some edge detection, but ultimately, most of the stuff we're interested in vision sort of happens further along the visual stream. And we'll have 3 talks today that at least start from that tradition or way of thinking about V1. The other approach, by contrast, emphasizes feedback connections to V1 and looks at purported evidence of cognitive processing and multisensory processing. And by contrast, under this account, right, V1's thought of as a place where, in some sense, feedback signals sort of come back together. Okay, it's more of an endpoint than a starting point. And we'll have, again, 3 talks that sort of highlight this more cognitive tradition to V1. But one of the questions you might ask yourself is do we really need a GAC on this, right? Because on the one hand, if you dig deeper into the literature, you have someone like David Heger on the more traditional approach to V1 saying, well, look, you can think of V1 in more Bayesian terms. And you've also got someone like Lars Muckley saying, well, look, you can also think of V1 in Bayesian terms. So perhaps the disagreement isn't as large as we think it is. But I think we need a GAC for two reasons. So the first, most obviously, is that, not everyone may sign up to this Bayesian account of V1. But the second, and more fundamentally, is I believe that people on this side of the fence just have a fundamentally different conception of V1 from people on this side of the fence. Because I would argue that people on this side of the fence think of V1 as, in some sense, an internal model of space. Okay. So this started with David Mumford in 1996, and I'll sort of read the quotation. He goes on to say, the role of V1 is not as the first processing stage of vision, but as the one and only high-resolution visual buffer in the neocortex, which is involved, and this is a key point, in all computations, which need high resolution, such as recognizing objects. We also see this in Wolfsamer and de Lange. So if you've got a cognitive task that needs high resolution, like working out which of these chords belongs to which object, you really need to bring V1 into the equation. You've also got Li Xiaoping's early work, arguing that V1 functions as a sort of saliency map. And you've also got this idea that if you've got multisensory processing, as Lars is going to highlight, so if you've got vision and sound being processed together, that might suggest that they're being integrated in some sort of 2D or 3D space. Good. So this is essentially the question we're asking when we're asking, is V1 a cognitive map? We're asking, is V1 acting as an internal model of 2D or 3D space? And so what I thought was worth doing before we brought everyone on stage was just to ask the community. So we sent this out on Twitter, we sent this out on a bunch of vision science mailing lists. And I'll be honest, it caused quite a stir, because what we found, well, not really to our surprise actually, is that there's no real consensus on how people think about this issue. So you've got a good chunk of people who are quite wedded to the traditional way of thinking about V1. You've got a good chunk of people who think of V1 in Bayesian terms. And then you've still got a good chunk of people who say, well, look, actually, I think it could be an internal model of 2D or 3D space. Perhaps it reflects conscious visual perceptual experience, perhaps post-perceptual cognition. Good. So there's an issue to sort out here, and we're going to try and sort it out today. And we're going to do it with 6 talks followed by a discussion. So we're going to start with David Heeger and Lars Muckley, sort of setting the landscape for the sort of no and yes camps. Then Henrike Nieborg and Andrew Parker are going to argue against the more cognitive interpretation of V1, followed by Li Xiaoping and Paolo Papale in favor of it. So without further ado, let's start by handing over to David Heeger from New York University, who's going to tell us about models of V1, a brief history. Thank you.
All right, hello everyone. I hope you can hear me okay. Thumbs up, wave, something. Okay, I will assume that you're hearing me. I have a lot to cover, 6 decades worth of work in just 12 minutes or so. So this is going to be quick. First of all, I'd like to apologize that I'm not there in person. As some of you know, I've been struggling with long COVID for a couple years, more than 2 years. Long COVID affects something between 5 to 10% of the population. So whether you realize it or not, you know someone with long COVID. I wrote up my experiences last fall, and I've updated it a bit since then. Please take a look, read through it, share it with anyone, everyone who might find it helpful. Okay, no talk about V1 can start without Hubel and Wiesel, so here you go, data from Hubel and Wiesel. Move on. Following their discoveries, in the 1960s, John Robson, Fergus Campbell, Colin Blakemore, many others through the 60s and early 70s proposed a linear systems model for the orientation selectivity in primary visual cortex. in which each neuron has a receptive field that computes a weighted sum, positive weights, negative weights. If a stimulus lines up with the positive weights, you get a big excitatory response. If it hits both the positive and negatively weighted subregions of the receptive field, you get no response at all. All right, so great starting point. Tons of work that was done on that, testing this idea of linearity. On the one hand, there was a lot of support for it. On the other hand, we'll see that there were also some serious problems with it. But the idea grew into what we would now refer to as a subband transform, or in modern parlance of machine learning, a convolutional neural net, in which you have convolution masks that are tuned for different orientations, different spatial frequencies, in which you can imagine there being neurons with different receptive field positions, but the same substructure. So a bunch of neurons that have these receptive field weights that tile the visual field, giving you what John Robson called a neural image. So this is the input image. That's the output of convolving this image with that convolution kernel. This is the neural image you get by convolving that input image with that convolution kernel, and so on and so forth, right? These, early versions of this used Gabor filters. These happen to be what Ted Adelson and Bill Freeman called steerable filters, and that together with Ted and Bill, Eero Simoncelli and I developed into what we called the steerable pyramid, to give you a rich representation of all of these different orientations and spatial frequencies. All right, 1970s, Movshin, Thompson, and Tolhurst 78 extended this with one important little trick, one important observation, which is, so here's your input, here's your neural images. The idea is that those feed forward into another set of convolutions, a layer 2 of neural images, so on and so forth, just like a convolutional neural net. The computation is just weighted sums. And then what Movshin, Thompson, and Tolhurst added to this is an output nonlinearity, and in particular a threshold or rectification. So if you ever do anything with a convolutional neural net that has a rectified linear unit, you should be citing this paper way back from 1978. It took the machine learning field a number of decades to catch up. Okay. A few years later, Ted Adelson and Jib Bergen replaced the hard threshold with a squaring nonlinearity, and used that to develop a model of complex cell responses. So you can think of each of these as a simple cell receptive field. You take odd and even phase, square them, add them together, and you get an output that they called an energy mechanism, which exhibits some degree of position invariance. So here's an example. There's an input image. Here's your linear neural images with the linear receptive fields. You take the sums of squares of the odd and even phases, and you get neural images that look like this, that don't have these little ripples near the edges, but just recognize essentially where the edge is. Not that they really recognize anything, but they respond where the edges are of the correct orientation. Okay, so now we're up to the 1980s. And again, there was a lot of empirical support for models of this sort or this sort. But there was also a separate, largely separate literature showing problems with the linear systems model. And this is when I was just getting into the field in the late 1980s, early 1990s. And from the computer vision field, where I had been working, amongst other things, with gain control, importing other ideas from engineering, right? The whole linear systems story comes from engineering, but gain control is another great idea from engineering. And it occurred to me that a kind of gain control that I ended up calling normalization might explain or reconcile the differences between this linear systems camp and this no, it's not that camp. And so the idea is illustrated here, that a given neuron has an underlying linear weighting function, but that its response is gain controlled or divided by the pooled response of a bunch of other neurons. that are nearby it with different orientation and spatial frequency selectivities and surrounding receptive field locations. You can write it mathematically like this, that the vector of output firing rates is equal to the underlying linear response, vector of linear responses, half-wave rectified and squared, divided by a constant plus a weighted sum of all of the other guys. And that ends up kind of shockingly capturing a very wide range of phenomena, empirical phenomena measured both neurophysiologically and psychophysically related to V1 and early visual processing, including some things that are illustrated here. The sigmoid-shaped contrast response function. Responses go up with contrast, but then level off. When you switch to a non-preferred orientation, that gets scaled down. Notice that the saturation does not occur because of the refractory period of the neurons. The neurons are perfectly capable of firing at higher firing rates, but they don't want to because they want to stay out of that regime in which they get clipped, in which they can't fire more spikes, and this gain control avoids that. Another phenomena that you find is what's been called cross-orientation suppression or surround suppression. This is the contrast response function you get to a preferred orientation on its own. This is the contrast response function you get if you superimpose either an orthogonal mask or a surround stimulus that suppresses that neuron's response to its preferred stimulus. On this log contrast axis, this looks like a shift to the right, which is a divisive or multiplicative effect. Okay. So now we're up to the 1990s. Fast forward another decade, and with John Reynolds, he and I came up with this idea of modeling attention simply by another gain control. Critically, the gain control happens before the normalization step. So you multiply by a big number here for this stimulus receptive field location, smaller numbers here. And then that gives priority and boosts the firing rates of the neurons that respond to that location, which effectively suppresses through the division the other neurons, which I've labeled here as responding to distractors. The idea of putting normalization and attention together was bubbling around in the field when we published this. The general similar idea was proposed by John Mounsel's lab and Jeff Boynton's lab. Critically, the thing that we did differently was to multiply by these attentional gains before normalization, which when you do that, again, captures a kind of oddly, shockingly wide range of empirical phenomena. Okay, let's jump forward a few more years since we've set this up as, can we do something Bayesian in this story? There's this beautiful pair of papers from Eero Simoncelli's lab showing that for environmental priors, right? So if there's a particular stimulus that's more prevalent in the world, that's what I mean by an environmental prior, that you can capture that prior just by changing the shape of the tuning curve. So the way that they express this, derive this mathematically, is to say that you want to maximize the Fisher information subject to a prior, a probability density, and with constraints that you have a limited number of neurons, capital N, and a limited total spike rate, capital R. And then the answer is that you warp the tuning curves to make them narrower for more prevalent stimuli, the ones that are more likely, and you make them broader for the stimuli that are less likely. And in fact, the gains, this is showing the general case that could have occurred, but when you do the derivation, the gains are constant. All right? So that's one way to add a prior to this story, and it just involves changing the receptive fields to effectively give you the tuning widths that you want. A different way to do this, which I call a context-dependent prior in this paper, is to have a hierarchical model that has both feed-forward processing and feedback processing with gates or modulators that allow you to switch the state so that it behaves entirely like a feed-forward system or entirely like a generative model feedback or like a combination of the two that allows you to combine feed-forward sensory signals, let's call that the likelihood, with feedback signals, let's call that the prior. And then you can switch it based on the context. So for one task, you can adopt one prior. For a different task, you can adopt a different prior. Or in an extreme case, you can just run this entirely feedback, and then it behaves like, visual working memory or visual imagery. All right, up to the current. I have less than a minute left, but I want to mention the work that I've been doing recently on organics, oscillatory recurrent gated neural integrator circuits that basically have, this is the membrane equation with two terms, an input gain times an input drive, a recurrent gain times a recurrent drive. This is just a weighted sum, the input drive. The recurrent drive is another weighted sum, but then there's another recurrence around that, which, suppresses the recurrent drive. The point is that this on its own causes recurrent amplification. This shuts down that recurrent amplification such that we now think of normalization as a dynamic recurrent process in which, instead of thinking of it as division, you think of it as less amplification. And you can write it as a system as a dynamical system in which you add noise to each of these terms. And unlike the conventional feed-forward thing, we now have this recurrent drive as well. And we can derive, because it's an analytically tractable model, closed-form expressions for things like the power spectrum. These red curves are closed-form analytical expressions showing peaks in the gamma frequency range. We can add attention to it, and again, derive closed-form expressions for things like the noise correlations between pairs of neurons. We can put this into a hierarchical model that includes feedback, like the PNAS paper I pointed at just a minute ago. And then we can derive, again, closed-form expressions for coherence between brain areas, communication subspaces between brain areas, and other results as well. The same model can be applied the same theory can be applied to model working memory, in which you get a power in different frequency bands depending on whether you're in the encoding or delay period stage. And we can also apply this same architecture to machine learning without even trying very hard. We're matching or beating LSTMs with a smaller model that is easier to train because of the intrinsic stability of having normalization. If you want to hear more about organics, I encourage you to go to these two posters, one this afternoon and the other one on Friday. And these are my various collaborators on all of this stuff. Thank you very much. Sorry I ran a minute over.
Cool, fabulous stuff. Next, we've got Lars Muckley from the University of Glasgow on multisensory and cognitive top-down contributions to V1.
Thanks, Paul, for organizing this, and David for a very nice talk and introduction. You for coming. I will use the 10 minutes to talk about the multisensory and cognitive top-down contributions to V1 by giving the landscape of what we find of feedback to V1. And I'll start with a bit of a neuroscience component to stretch the concept that cortical pyramidal cells, be the layer 5 or 2-3 pyramidal cells, are not integrate and fire, but are two-component neurons. And they have the feature that they can integrate in a synergistic way two streams of information, the feed-forward that reaches more close to the soma, and feedback stream that comes from neighboring and further away areas to the superficial layers, layer 1 and 2-3. If it would be an integrated fire neuron, then these 10,000 dendrites in the upper dendritic tree would have no chance and no influence because they wouldn't make it down to the spike initiation zone. But what these neurons are found to do is they have a backpropagating spike that then integrates whether there was some expectation, let's say, or some feedback, and they can integrate it synergistically. So either it starts bursting or reduces the fire rate. And so this gives the opportunity to see what comes in context of what is predicted. Now, where's the influence coming from? So if the target area here shown in green, a layer 5 pyramidal cell, receives from the neighboring areas by two streams shown in blue, either in the superficial layers, layer 1 or 2, 3, it's important not to only think about where the cells are, but where they are connecting, because that's where they boil off energy, which is what we measure with fMRI, or in the deep layers. Now, to investigate the kind of content, the content that is broadcast back to V1 from these various areas, and that's a general pattern throughout the cortex. There are 70% chance that any area is connected to any other area, regarding to 20, 30 years of anatomical research of the Kennedy lab. You can see these two streams coming in, and now the question is, how can we investigate them? We use the approach of silencing the feed-forward input to better tune in to the cortical feedback. And so we look into primary visual cortex, do retrotopic mapping, and then we show non-informative information at that spot. So these are the occluded regions shown here in the lower right quadrant. And in the rest of the visual scene, we show complex visual scenes of a street, industry park, or mountains. In this kind of paradigm, we have shown that there's activity, there's no activity when it's occluded throughout, but if you do multivoxel pattern classifier, you find information about the surround scene in the occluded area in the superficial layers, so that's shown here. By modeling what this information could represent, we tested various models. The one that fits best is a model derived by behavior. We superimposed 50 subjects that quickly sketched the kind of information that they would be expecting to be behind this occluder. And superimposed, you see these kind of line drawings. They match the best to the activity that we find in the superficial layers of V1. And so it represents, so to say, the kind of expectation that is lingering there to be ready to be read out. To confirm this kind of idea of the dendritic hypothesis, we need to turn to a rodent model. In mice, the same were recorded from layer 2, 3 pyramidal cells and layer 5 pyramidal cells, and confirmed cells that have a receptive field in this occluded area, for example, in this forest, would respond strongly if the whole forest is presented in the left case, but have only this smaller response, but significant response in the occluded area. It follows 30 milliseconds later, expected from the delay of feedback. These regions have another property, and that is, after intensive training, the mouse have seen the stimuli for 2 weeks again and again. The response pattern changes, so these expert mice, they now respond in the occluded case equally strong as in the normal case, in the full screen. So now they know exactly what to expect, and when it's not presented, they fire very strongly. So this resembles more the idea of a predictive arrow neuron that is responding. And this little icon shows you that these populations are not overlapping, they are not the same, so responding to feed-forward and feedback, they would be along the diagonal here, but they are either responding to the occluded or to the full image, consistent with representation of what's there, or a negative prediction arrow that only fires if something that is expected is not presented. There are a lot more to unfold in this study, but and Paolo will talk more about this in monkey studies. But and this paper is on bioRxiv and a live paper on Sonoda. The reference is missing somehow here, but there's a lot more to uncover. But for the learning, we compared it to a human experiment in which we showed these, for 2 runs, these kind of Mooney scenes. And then during the anatomy, we showed the grayscale. So now the head of, the head or the waterfall. And then we had another 2 runs, which we showed again the black and white screen. And so this is a one-try learning, if you like, or a few minutes learning. And after that learning experience, the feedback that can be extracted in the occluded area is now more enriched. So the similarity analysis of area V1, V2, and V3 after this grayscale is more dissimilar. Another experiment we show in the lab that in case of neon color spreading at the non-stimulated area, you have feedback to the superficial layers where you can decode the color, whether red or green. And if you ask the subjects to imagine a red or a green disk, then you can decode that in the deep layers. So that points to a different stream of cortical feedback that I highlighted earlier from further away areas. So to give a bit of a sort of these kind of examples I've shown so far, I align them from be very much vision-like to more cognition. So the kind of response pattern that we see in the feedback is either related particularly tightly to perception, like in the illusion case of neon color spreading, filling in amodal completion of a mental line drawing, and in the imagery that is a little bit more liberated, so the context doesn't precisely determine where to imagine it, even though we instruct our subjects, but there's more freedom, so it's more on a top-down drive. And I will now move 3 quick examples in which we liberate more from the language of V1. And the question, so up to here, I think it's very compatible with the model David Heeger has presented in PNAS, and would describe that as the top-down drive that modulates on the properties of the features that V1 is representing. But the question is, what is the content of the top-down drive? If it comes from other sensory areas, is the feedback to V1 translated to the coding language of V1, or is it maybe contributing in a different way? So here's an example from navigation. There's also a rodent experiment that goes along with that, not from us, from Kay, showing that mice anticipate where they will be turning. Here, Matt is walking through a maze with, like all our subjects, for 30 minutes, learn to navigate through this virtual flat. And then in the experiment, they are shown pre-recorded movies of navigation, and they know exactly what to expect. And during the experiments, we occlude one part to silence the feed-forward input and to read out from the feedback. And what we can see, and I'm diverging from the topic now, it's not in V1, but in V2 and V3 retinal topic areas, we can see code that is anticipating the room the subject is going to. Another example, feedback from a different sense, is this example. We've blindfolded our subjects, so no feed-forward input to V1, and we present them with these auditory stimuli. And we can decode the auditory scenes in V1 and more in the periphery than in the fovea. We have replicated this experiment with 10 congenitally blind subjects, so this has nothing to do with visual imagery. They have never seen any visual input, and they have the same pattern. So in the extra and also in the periphery, it's stronger than in the fovea, and everything is really expanded, consistent with the idea that there's cortical feedback to V1, especially in the periphery, that is exploited because feed-forward input is missing. In normal subjects, it's combined, but the question is, what are these code combining? And here, in a very new replication, we use aphantasic subjects, and there we can replicate a little bit of decoding in the periphery of V1, but in general, there's a great reduction, which I think is consistent with reduced cortical feedback across the domain. And the last example is, I want to remind you to a study from Cambridge's lab, and Williams has instructed subjects to fixate and to make judgments about these objects in the periphery, whether they are blobby or spiky. And when this is the task, then it can be decoded in the center, whether the content of these objects, not if it's not the task and not in any other place. We replicated this with more natural scenes. If you make judgments about the objects that are showed in the periphery, and if this is task relevant, you can decode it in the fovea. In all other situations, you can decode the scenes. So putting this together, I've shown you different examples of feedback from auditory, from navigation, from cognitive tasks that can be decoded or read out in the often in the superficial layers of V1, or in the deep layers, or general when we average over V1. It's consistent with the idea that you have a hierarchy in which first the signal gets distributed through the cortex and you receive expert feedback that comes back. But the question is the code different? And what are the advantages if you combine different codes from motor cortex, somatosensory, auditory, and is there a purpose for that? Jeff Hawkins argues for that when he designed object representation and grabbing for an object like a coffee cup and so on. He noticed that it's very advantageous to have a representation of grid cell-like features combined with the feed-forward input to achieve more robust networks that are capable of doing different tasks. And so I think there's a case to be made. And with this, I'll stop. Thank you.
Brilliant. So next up, we've got Henrike Nieborg with from the National Eye Institute with minimal contribution by body movement, but effects of spatial attention in V1.
Okay, so thanks, Paul, for putting together this GAC. So we have just heard from Lars about multisensory effects.
Sorry, Henrike, your video isn't on. If it's able to be switched on. Or,
oh, is not?
Oh, sorry.
Okay.
Yeah, if it's not an easy fix, we could see your slides, but we couldn't see you, so.
Oh, you couldn't see me. Okay. Yeah, sure. Sorry. Yeah. Better? Okay, sorry. Yeah, so we've just heard from Lars about the multisensory effects in V1. And we were interested in a particular type of multimodal effect, and that's the effects of the body movements, an animal's own body movements. And this question was really motivated by recent work in mice that showed that spontaneous body movements had a very pronounced effect on neuroactivity brain-wide, including in the primary visual cortex in the mice. And these findings, I mean, Lars has already sort of alluded to some of them. They really generated substantial interest because the effect size was really very impressive. But also they obviously relate to important questions, including that about whether V1 does have a cognitive map. And so we were interested in addressing this question in a primate model, and the model we use is the macaque monkey. So we asked exactly that question for macaques, and we used two types of visual tasks. One was a visual fixation task, and the other combination between discrimination, a combined discrimination and spatial attention task. And we had macaques seated in primate chairs, and we were recording from the primary visual cortex and also V2, V3. And we had two cameras that monitored the monkey's body movement, sort of pointed at the trunk, the other pointed at the face. And so just to convince you, even the monkeys are seated in a primate chair, they do move, so we had movements to work with. And we used a way to quantify the movements that was also motivated by work, inspired by the analyses that were done in mice, so singular value decomposition that gave us movement components, and we then projected the movie back onto these components, and this is these mood traces. And to convince, so you can see here how these time courses relate to plausible movements of the monkeys. For instance, this F2 component are movements around the eye, and similar for instance, movements around the mouth. So we had ways to quantify these movements. We could then relate this to spiking activity in these visual areas. And we did so by fitting a multivariate regression model that was also similar to the ones used in previous work in mice. And so we had task regressors, in particular stimulus, and then we also had the top 30 movement components for both the face view and the view targeting the trunk. And we had a slow drift regressor to take out very, very slow fluctuations or non-stationarities in spiking activity. And the power of using this modeling approach was really that it allows us to look at the trial-to-trial variability, especially when things are different across trials, such as, for instance, the movements. So we computed the cross-validated variance explained that was uniquely explained by the movements, but not by any other covariates. And we refer to this as the unique variance. And here it's the average unique variance across all the V1 units. And we see that on average, movements do significantly, or did contribute a significant, even small fraction, but significantly did contribute to variability in V1. So at least qualitatively, this looked similar to the results in mice. But then there's a wrinkle to the story, and that is that we actually had different epochs. So the monkeys were required to maintain visual fixation, and then we had these intertrial epochs. And during these fixation epochs, the retinal input was under experimental control, but not so during these intertrial epochs. And the analysis that I've just shown you was actually for those epochs when the retinal input was not under experimental control. When we did the same analysis for these epochs when the retinal input was under experimental control, even these small contribution by movements completely disappeared. So, yeah, and it was highly statistically significant. Now, we had recorded one camera pointing at the face, the other at the body, and this had, oh yeah, so when retinal input was known, the movements did not predict spiking activity. And so when we did this analysis separately for the two cameras, we found that the camera pointing at the face really replicated this mind finding, but for the camera pointing at the trunk, we found that in either epoch did we see any variance explained by these movements. So to summarize this part, we found that only these facial movements, but not the body movements, contributed to this neuronal activity, and only during these epochs when the retinal input was not under our experimental control. Which led us to wonder that this could have something to do with the eye movements. Now, to address this, we did an additional analysis. So we had measured separately the eye movements, but in the previous analysis we had not put them into the model as additional regressors. But when we did so, then that substantially reduced the variance previously captured by this camera pointing at the face. So including these eye regressors really explained away the variance due to these spontaneous movements. Now, what about eye movements when the retinal input was kept constant? To do this, we leveraged the fact that we knew the receptive field positions of all the units we recorded from, and so we could separate these three viewing epochs into some in which we could infer the retinal input, and to others where we could not infer it because the eye movements took the receptive field outside of the display. And when we did this, we also found that inferring the retinal input again reduced the variance previously explained by these facial movements. So inferring the retinal input during these viewing epochs also explained away variance due to these movements. And just to compare the amount of variance in these uncontrolled retinal input epochs to the overall variability captured by other covariates, uniquely captured by other covariates. This here is the comparison where, so just note the different scale. So basically the standard model, but mostly the stimulus model, but also including spatial attention, really accounted for much more variability by an order of magnitude more. And so finally, we were wondering how much, how these effects compared to the well-known modulatory effects by spatial attention. So here we just plot the PSDHs, so the average stimulus triggered activity during the trial when the animal was either paying attention towards the receptive field or paying attention outside of the receptive field. And we find this characteristic modulation by spatial attention. When you do additionally, when you additionally separate the trials according to whether or not the monkeys moved, we found no additional modulation by these movements. Not surprisingly, because we hadn't found any movement related modulation. But this allowed us to really directly compare these effects. And we then also computed these classical kind of modulation indices where the difference of the responses, so the mean response when attention was paid towards the receptive field minus when attention was paid outside of the receptive field, divided by the sum of these responses. This is the attention index and an equivalent index for these movements. And then we find the characteristic shift towards positive values for attention. So, but for these movements, they were really all hovering around 0. So we do find significant modulation by spatial attention, as has been done many times previously, but we found really virtually no modulation by these spontaneous body movements. Now, then to summarize, so for V1 in macaques, movements largely do not modulate activity, and this finding is quite different from the previous observations in mice. But also, in contrast to this absence of modulation by these movements, so the sort of type of multimodal responses, we do also find these modulation or significant modulation by spatial attention. And finally, something that may seem obvious, but I think is really relevant in this context of the gag, is I think our study also is a reminder of the importance of really accounting for these effects by eye movements, because these eye movements really or maybe also body or gaze movements that can change the retinal input in very systematic ways depending on the cognitive factors, and they may thus mimic actually cognitive contributions to the V1 activity, but can actually be explained in the ways that we understand as just being responses, sort of these feed-forward responses to the changed retinal input. And with this, I'd like to thank my group members, and in particular people who contributed to this study, and the two first authors here highlighted here in yellow, Injil Kang and Bharat Taluri, who is also contributing to this gap. Thank you for your attention.
Fantastic. Next up is Andrew Parker for the Against team on the neuronal representation of binocular depth in V1 is cognitively incoherent from the University of Magdeburg.
Okay, well, thanks to Paul and the organizers for setting this up, a really interesting debate opening up already. I'm going to talk about binocular depth, and I'm going to make the claim that actually the representation in V1 is, in a sense, cognitively incoherent. I'll explain that as we go on. So the cognitive theory, as I understand it, Paul has given an example from David Mumford, is something like this, that analysis by synthesis explains an observed data set, a vector, an image, in terms of a compact set of hidden labels. And similarly in Rao and Ballard, predictive coding, a model of visual processing in which feedback connections from a higher level to a lower order visual cortical area carry predictions of lower level neural activities. And the feed-forward predictions carry the residual error. Well, we don't have to imagine what that looks like now. I've put a description into one of these dreaded art generation AI programs, and my description is over there on the right, lake with trees to the left, mountains to the right, sheep eating grass by the lake, and no cars, no cows, those are my exclusions. This is the image that it comes up with. And I think this is the model that is envisaged when we think of a model of the world being transformed back into an image. In detail, it might be wrong about the number of sheep or the exact position of the clouds and so on, and V1 would tweak that and send it back up for further processing. One of the issues is that that conception suggests that there is a simple image in V1 which is capable of being tweaked and altered and sending back feedback. This is a very different view of, indeed, our perceptual field. As I'm looking at you out into the room, I've actually got two images of this microphone that's in front of me. And this was captured with this binocular painting by Harold Hayden from Chicago in the 1950s. He took it very seriously as a new way of delivering art. He thought it as a competitor to Cubism. And he tried to depict the perceptual field with all the elements of double vision within it. He actually guarded this rather seriously at one point, thinking people would steal the idea and paint lots of pictures. Obviously, that didn't happen. It didn't catch on in quite that way. What I want to show you now, though, is that there is a serious matter about multiple matching. It's a long-standing matter in binocular vision, and it's illustrated here by this diagram from Baylor-Uleth. So we simply imagine that each eye, the left eye here, the right eye over there, looking at 4 dots in a row. 1, 2, 3, 4. And it seems simple enough that we actually just see 4 dots. But Uleth realized that if those dots are identical features, then the brain has a matching problem, which is to say the dot along this L1 here, along this line of sight from the left eye, could be matched with R1, but it could also be matched with R2, R3, or R4. And he pointed out that the brain has to sift through those and assign them. And what I'm going to show you is that actually in V1, the representation contains not just those matches that we perceptually see, but actually the other ones as well. So the way that we do that is with an awake behaving monkey who is trained to look at these images in a stereo viewer. So this is the left eye's image here, and the right eye's image. There's the fixation point, which obviously fuses into a single fixation point. That disc, with the sinusoidal grating inside it, has a particular depth plane. And if we move the whole disc, here as in B, to a new position in one eye, then we shift the whole disc and the bars, they all shift in depth to a new depth plane. Diagrammatically, what you have here with the red is the receptive field of a V1 neuron that we're recording from. And that stays in the same place. It's stuck on the retina with a retinocortical projection. As a consequence, when we shift by this across by a certain amount, we get to a position where this black bar in the B case here is in exactly the same position as it was in the A case. In other words, the local features are the same, but the global percept, that is to say, the depth, is different. We can control the depth percept. This has actually been done quite nicely by Suzanne McKee and collaborators, and as they shift the outside boundaries of the contour, then it shifts accordingly in depth. So what happens in V1? Well, what happens in V1 is that we get a peak of the tuning curve for a cell here. The random dot stereogram produces a tuning curve, and we can think of that as being the global valid match. But over here we get a secondary peak, which corresponds to the position of the second bar entering that receptive field. Here's another example from another neuron. And the position of these depend upon the feature contour of the stimulus itself. So that's shown here. On the right, you see a measurement with the bars of the grating are at 1 cycle per degree and at 2 cycles per degree. And you see the secondary peak shifts according to the feature which is falling on the receptive field of the neuron. That's summarized here. The position of the fitted horizontal period and the horizontal period, they are linked to the actual local feature in the display. Now, that is suggesting that all of those are visible within V1. This is not much of an experiment unless I've got a positive control as well. And we've got two elements of positive control. First, we tested the monkeys to make sure that they did actually do psychophysics in the same way that the humans do. And sure enough, for locally equivalent stimuli here and here, they're reliably saying those things are at a different depth plane than where the features are lying in V1. And second, in V2, if we move out to V2, we find neurons of this type in which the where we expect to find a secondary peak, there simply isn't any. This is a V2 neuron showing full suppression of the responses to local features. We can elaborate that a little bit further and look at the tuning to random dot stereograms and the tuning to the disparity grating there, and that is indeed aligned. So those neurons are showing the concordance we would expect according to the perceptual responses. Another one of the same type. And we can also measure the extent to which neurons suppress the secondary peak, the A2 peak here. The amount of suppression you expect varies. Now, this is actually a V2 neuron, so it's behaving like one of those V1 neurons. It's actually showing those secondary peaks. But actually, if we look at the attenuation, we find that almost all the V1 neurons attenuate substantially. There's a few of them out there that I can discuss later if people want to, but many of the V2 neurons are showing substantial attenuation. And that's consistent with a lot of other evidence that there's a step change in binocular processing from V1 to V2. This is the same thing for the horizontal period that we had there. So in summary, the V1 binocular neurons are responding to individual features, multiple candidate matches, and in a sense, they're cognitively incoherent. They actually allow the same feature or object to be in two places at the same time. And I suggest that that doesn't actually fulfill an adequate definition of what a spatially cognitive process is. I also note that the binocular energy model that was mentioned earlier actually shows this behavior. That is a valid model of V1 processing. And at least some V2 neurons show responses to globally consistent depth. So I'll stop there. Thank you.
Brilliant. Thanks so much, Andrew. So next we have Li Xiaoping from the University of Tübingen. Xiaoping's actually on the Zoom call, but we didn't trust the Zoom connection she has. So we're going to try and run a video instead. So let's see if...
Bring it off for a second. Go to stone.
Fantastic. Let's give it a go.
I like to argue for multiple roles for V1, motivated by the attentional bottleneck that makes us inattentionally blind. The standard model of V1 sees V1 as more or less passive, outside the more important and complex tasks for vision. Most ideas about V1 ignores the information bottleneck. We perceive only a tiny fraction of visual inputs, mainly the inputs within the attentional spotlight. This spotlight is selected mainly by a gaze shift. This visual location was in the peripheral visual field before the gaze shift. I have proposed that a saliency map is created in V1. The hotspots in this map attract gaze shifts exogenously. Therefore, peripheral V1 computes saliency to guide attention. It motivates the idea that the bottleneck starts right after V1. The bottleneck makes the information impoverished, so that recognition can be ambiguous. Even in central vision, one may be uncertain, for example, whether this is a red flower or a red apple. More recently, I proposed that central vision can send a feedback to query for additional information, particularly from V1, to resolve the ambiguity. This is as if to look up information from the blackboard. However, I hypothesize that this happens only in central vision due to limited brain resources. So there's a functional difference between central and peripheral vision. Therefore, central V1 is for recognition, which is helped by the recurrent feedback query. The bottleneck motivates both the V1 saliency hypothesis and the central-peripheral dichotomy theory. A diagnostic type of information lost downstream from V1 is the information about the eye of origin of visual inputs. This information is invisible to perception. Human observers cannot tell whether visual inputs are shown to the left eye or the right eye. But this information is available in V1, which has many monocular neurons tuned to this information. But this information is lost in V2 and further downstream areas because they have only binocular neurons. A convincing evidence for the saliency map comes exactly from this eye of origin feature for saliency. In this image, human observers are asked to quickly find a uniquely oriented bar. This is an example when all these bars are shown to the left eye only. If one background bar is shown to the right eye instead, the perceived image is unchanged. This bar, unique in eye of origin, is not distinctive at all to perception. However, in most trials, the first saccade is directed to this non-distinctive bar before saccading to the search target. This is as if this non-distinctive bar has a unique color, but only V1 is not colorblind. This behavior is a fingerprint of V1 for saliency and has been replicated by other labs. Another evidence comes from an experiment in which a monkey tries to find an uniquely tilted bar to saccade to it as quickly as possible. Meanwhile, we record from V1 neurons responding to the target bar. This plots the neural responses versus the time since the bars appear before the monkey makes the saccade. This is the average response from trials with a faster onset of the saccade. This is from trials with slower or incorrect saccades for the same visual input. Their difference should therefore be associated with the saliency difference in behavior. This difference is significant at a very short latency of 40 to 60 milliseconds, too short for the saliency signal to arise from feedback from any downstream visual regions. Evidence for the CPD theory includes many illusions that are only visible in peripheral vision. Here is an example. You see illusory motion in a static image, but not at where you fixate your gaze. Your peripheral vision lacks the feedback to look up the V1 blackboard, so can be easily fooled by information impoverished feed-forward signals. Central vision is not fooled because it has the feedback query to verify feed-forward signals. We predict a new illusion, the reversed depth illusion. This is illustrated by a 3D depth difference between a disk in front of a ring. Both depth surfaces are covered by random black and white dots. This scene is depicted by a random dot stereogram, giving a veridical perception of the disk in front of the ring. The reverse depth illusion arises when we revise this stereogram to give an anti-correlated random dot stereogram, in which, for the disk, each black dot in one eye corresponds to a white dot in the other eye. Such a disk is nonsensical. But V1 neurons tuned to depth are fooled. They respond as if the disk is behind the ring. In other words, these V1 neurons report to higher brain areas that the disk is behind the ring. Central vision does not get fooled. It sees the disk as neither in front nor behind. But peripheral vision sees this reversed depth illusion reported by V1 neurons as theoretically predicted. A second prediction naturally follows. This reverse depth illusion should become visible in central vision when the feedback query is impaired, so that central vision also cannot query the V1 blackboard to veto the fake news reported by these depth-tuned V1 neurons. This prediction is confirmed. The feedback is compromised using a visual psychophysics trick of backward masking, which quickly removes the original visual inputs to make them unavailable for the feedback query. This backward masking is achieved by making the random dot stereogram dynamic, with a very short interval between successive frames of the dynamic stereogram. Therefore, V1 has multiple roles in vision. It creates the saliency map to guide attention. It starts the information bottleneck, and is a critical player in the feed-forward feedback network for visual recognition in light of the bottleneck. This framework provides a fresh perspective on how vision works. In feeding forward information for visual recognition, it resembles the standard model of V1, but adds that the feed-forward information is massively limited by the bottleneck. Its feedback query can be related to the idea of V1 as a blackboard or high-resolution buffer. However, our feedback query is motivated by the presence of the bottleneck. Additionally, this feedback query is only or mainly for the central visual field. The feedback is to query for additional information through the bottleneck in order to help the particular ongoing recognition, using the algorithm of analysis by synthesis. This feedback is not for predictive coding. This framework has provided highly non-trivial and falsifiable predictions, some of which are already confirmed by data. Current and additional predictions provide further opportunities to falsify or revise this framework. So far, it has withstood the substantial test of time.
On Zoom, she'll be part of the discussion. Good. So then that just brings us to our final speaker, Paolo Papale, on Is Cognition the Dark Energy of V1?
Thank you. Okay. Thank you, Paul. Yeah, I think so far, probably the most popular views is this difference between the peak response explained by the standard model and the late response dominated by top-down feedback. But I think there are at least three elements related to the feed-forward models of V1 response that need to be discussed, because I think there is no agreement from the field The first one is about the standard model itself. I think there is no standard model, there is more of a standard intuition. Meaning, I think everyone in this room has a standard intuition of what V1 is doing, mostly based on orientation, contrast, and so on. And it's pretty easy to start writing equation from Gabor patches, trying to model the V1 Fivora response. But as soon as you try to add some canonical computation, division normalization, surround suppression, basically there is no standard formula anymore. So I think we are lacking a standard definition of V1 response. You can basically find different formulas and different equations and different interpretations in many different papers. The second problem is what we call the dark energy of V1. So you record from a V1 neuron. You show gradings to the monkey, for instance, and you use the responses to have an empirical estimate of the parameters for your own standard model of choice. And then in the same session, you record responses to natural images. You can use your standard model to extract energy from those natural images and try to predict the response to natural images. And you can start with simple and complex self-models, and you're going to see that you don't explain a huge amount of variance. You can add canonical computations, and you're going to improve your performance. You're going to still see a lot of unexplained variance. Or you can go all the way with activations from pre-trained neural networks. And you're still going to end up having between 40 and 50% of variance unaccounted for. And this is sort of an equivalent in our field of dark energy, meaning this is an energy that shouldn't be there. It's unaccounted for, and it's in the way of our full understanding of what V1 Fivora response is doing. Or maybe there's an alternative. It's just a mistake in the way we compute noise in response to natural static images. It's just because of low SNR, but we do know what V1 Fivora response is doing. But still, we need to agree on that as a field. And then there is a third point. As soon as you start working with natural images, you quickly realize how little, how much V1 energy seems to be completely orthogonal to our perception. So if you, for instance, look at the V1 energy according to different models, and you look at the top 10% activations, which are highlighted for this particular image by the color pixels, you immediately see that there is a lot of information there that is not useful to our understanding of the scene. And if you ask people to segment objects, for instance, you're going to see that there are borders that have a high V1 energy, but that we don't care about, and the other way around. And if you think of V1 as a sort of a bottleneck for downstream processing, you might think, okay, V1 is sending downstream a lot of information that we don't really need, maybe. And there is also behavioral evidence. I'm not going to go deep into this example from a paper from Peter Neri, but it basically showed that if you have to judge on local contrast, basically the behavior and your perception of what is a relevant edge, what is a relevant border in the image, which are mostly the borders between figure and ground, they're going to dominate your performance. And whether it's a high contrast or low contrast, for instance, or high V1 energy or low V1 energy element, that's not going to be of any help, even with short presentations. So we also try to look at this in a more systematic way in terms of response of V1 neurons. So we actually isolated patches from object borders segmented by humans and from patches that had the same V1 energy, but that were not, they were ignored by subjects. As you can see, this is multi-unit response from awake monkeys in V1. And there is quite a difference that emerged as early as the onset of response. So there is an enhancement when it's a segmented object, even for small local patches. And this is a significant effect at the population level. You see here both multi-unit from awake monkeys, but you also see single unit from anesthetized monkeys. So this seems to be sort of an automatic process. But overall, this is probably not what we're looking for in terms of explaining the dark energy of V1, because the average effect is, in both cases, around 5%. So to go back to the question that is the title of my presentation, is cognition the dark energy of V1? We don't know, but I think there is some hint that object segmentation, or at least what matters to perception, might be the explanation we're looking for, but so far it looks like it's not enough to explain it. But I think we could agree on the fact that we probably need more and better data sets and not just models and definitions. And with that, I would like to thank you.
Brilliant stuff. So now we're going to transition to the discussion part of the session. So if we could bring everyone up on Zoom, and if everyone switches their cameras on as well. And then we've got the existing 3 speakers here. So primarily, this was an opportunity to hear from all of you about your thoughts about V1. We've had some very different opinions shown today. So if you'd like to come up to use either of the microphones at the front to ask your questions, identify yourselves, say where you're from, if you fancy. We've got the 3 speakers you heard from remotely before. We've also got Pieter Rosema and Tony Movstrom joining us remotely. But as we wait for anyone from the audience to ask questions, this is my reflection on the GAC so far. I was just trying to do a quick count. We may need, rather than 2 camps, something that feels like maybe 5 or 6 different camps. People respond to that. So there did seem to be, initially I thought there was a lot of consensus, saying, look, V1 may be doing something Bayesian, coming out from both David Heger and Lars. But then Andrew came in and said, well, look, you're sort of discounting the fact that really we've got these sort of fundamental matching problems, and so anything that feels like that kind of processing, not misinterpreting you, really doesn't seem to fit with that account. So that's 2 camps. But then the 3rd camp, Lars came in and said, well, but also, I've shown you it's not just limited to visual processing. Like illusions is also extending to more sort of multisensory and cognitive processing. Henrika was also quite similar to Andrew. Xiaoping said, well, look, I'm happy to think of analysis by synthesis, but I'm not happy to think about predictive processing. And then Paolo came in and said, well, look, all of you people are thinking about feedback to V1, but I want to talk about feed-forward stuff and the potential cognitive signals that are hidden in there, right? So if that's an overview of what the different viewpoints are, I don't know if any of the other speakers had any thoughts or reflections on each other's talks, and also Pietro and Tony as well, if they had any thoughts. I don't know who wants to go first. Anyone from in the room?
I'm really hoping for some feedback from the audience to resolve some of these things.
Can you hear me?
Oh, yes. Peter, yes, definitely.
Yeah, so I would like to share some thoughts. So I think there are some topics on the table, and I was surprised. I think there was more consensus than I expected. So most people seem to agree that there are top-down effects in V1 and that they play a role in attention. I think Paolo briefly alluded to it, that they also play a role in figure ground, and of course these things are intertwined. Now, if you reflect on the question, is V1 a cognitive map? If you have attentional signals there, of course, you can use them as a cognitive map. For me, the question is it the cognitive map? And I would suspect it's probably not the. I think there are many cognitive maps in the brain, and the ones that are important for your behavior really are task dependent. And I would like to give one example. So recently we studied in monkeys, but also in mice, a task in which the animals had to detect something, just a dot of light on the left or on the right of the screen. And in the second task, they had to do figure ground segregation. So they had to see a figure that was different in orientation from the background, either on the left or on the right. And we used optogenetics in mice. And what we found is if we knocked out the entire visual response, the feed forward and the feedback components, then the mice, of course, couldn't do either task because they need V1 for that. But if we then switched on the optogenetic inhibition after the feed-forward response had passed, so the higher information, the higher areas had been kind of informed about the visual stimulus, then if we silence later, basically knocking out these late spikes in V1, then the mice could do a luminance detection, but they couldn't do figure ground. So that's where I think in the figure ground task, V1 is a cognitive map. And for me, the luminance detection task is one of these tasks where V1 is not a cognitive map because we don't need it. And maybe that's giving a direction to think in if you are looking for a resolution of the talk of Andrew Parker, who also demonstrated that there are definitely some conditions in which V1 activity is maybe not mapping one-to-one to perception. Although I was intrigued, I thought that V1 looked more than to V2 than one might have anticipated. So this dichotomy between V1 and V2 was not so absolute as was presented by Andrew, was my observation.
Cool. I think Tony wants to come in on this point.
Well, perhaps not so much on Peter's point, but I wanted to make a couple of observations, one of which was provoked by Peter, and the other of which was related actually to something Hendrika said, which I wanted to emphasize. To Peter, I simply wanted to say mice and monkeys are not the same. We know that the architecture of monkey and mouse V1 are very different. The connectivity of monkey and mouse V1 are very, very different. I think there is a case to be made for studying both of them. But I think there's not a case to be made for taking results from one and assuming automatically that they will apply to the other. I actually happen to think that that experiment Peter described with the optogenetic blockade of the trailing spikes in V1 would work very elegantly in monkeys. I'd love to see it done there. Unfortunately, we can't yet do it. But there are many other things in mouse. For example, as Hendrika showed, strong responses to the animal's movement in mouse V1, which are absent in monkey. Marshall Schuler years ago showed strong reward signals in V1 that are absent in monkey, and so on and so forth. So let's just keep monkeys and mice separate, and I think I will make the claim that monkeys and humans are similar enough to be spoken about in the same breath. I'd be happy to debate that. The second point, and I think one that's perhaps most important, is one that Hendrika was maybe a little gentle about, and I want to be a little less gentle. And that is to say that these experiments are extremely challenging. And the reason that they're so challenging is that you have to be absolutely certain, especially in monkeys, especially when you're talking about the center of gaze, that you know exactly what's happening on the retina. So when you set up two different conditions, you have an attentional condition for this, you have a figure ground condition for that, and so on and so forth. If you don't know exactly where the monkey is looking at all times, the possibility exists that the difference you observe will not in fact have to do with something by way of elaborate CNS processing, but will simply have to do with the fact that the monkey's eye movements are subtly different in the two cases. John Mansell demonstrated this many years ago when comparing V1 and V4 attention effects, and demonstrated, as I recall, that most V1 attentional effects, as they were then described, actually emerged from different oculomotor patterns that did not have comparable effects in V4 because the receptive fields were larger. So it's not that there aren't interesting things going in, it's not that there isn't top-down feedback, but one thing to remember is that one easy way for higher centers to influence what V1 does is by changing where the eyes are and by changing the signals that are coming into the retina. And I think that's interesting, although probably not interesting in the context of this particular debate where people are thinking more about neural circuits than oculomotor visual circuits. That's all.
Cool. Wonderful. Thanks so much. I think we've got a question from the audience.
Hey there. I don't know, can they see us? Hi, it's Ruth Rosenholtz. So quite a bit of the discussion has been about feedback and whether or not feedback to V1 implies what the nature is of it and whether or not it implies that V1 is a cognitive map. And then Xiaoping has sort of thrown a wrench into the whole thing by suggesting that feedback might be quite different in peripheral vision than in central vision. It seems to me like some of the rest of you might have some comments on that. David Heeger, for instance, do you need to run the normalization model of attention differently when you're talking about peripheral vision than when you're talking about central vision? Lars, do you have to decode differently in peripheral than in the central vision? Do you not have those pyramidal things in peripheral vision that you have in central vision to integrate feedback information? Is it different? Is there reason to believe from the physiology or from the modeling that peripheral vision is different?
Sure. Well, I think Tony wants to jump in on this point.
So if somebody asked me a question about peripheral vision, I would find Ruth and ask her what the answer is, because she is, as far in my view, the expert on the subject. But if I can sort of crudely summarize a lot of what she says, there is a difference in the way peripheral vision works in the sense that it provides much more something that looks like a statistical summary of what's going on locally and much less a figural set of figural information. So I think there's every reason to think that the periphery is different from the fovea. Whether that is different in V1 in any material way other than in magnification, I think is the key question. And I do think that the point I made earlier about knowing what's going on the retina applies especially to central vision and perhaps less critically to peripheral vision, where the receptive fields are larger and sensitivity is less. And, you know, people like Ruth have told us that what we really do with the periphery is to measure statistics rather than objects and things of that sort. I'm putting words in Ruth's mouth, but she invited that by standing up and putting words in ours.
Should we go with David? And then I think Andrew Parker wants to jump in on this particular point. Thank you.
Just wanted to follow that up with a further point about V1 binocular vision and extra striate binocular vision. It might be in many people's minds this is perhaps a difference also not just between mouse and monkey, but between neurophysiology and imaging data. And I wanted to point out there is actually rather clear imaging data from Serge Dumoulin's group looking at population receptive fields and showing that there is a distinct difference in that V1 is showing population receptive fields relating to retinal structure, and there is in extrastriate areas there is a cyclopean representation of the binocular stimuli, and that again is a transition which between V1 and V2 that's there in the imaging data as well. There's actually a set of other observations for all of this, and I think that we may have to accept that simply putting a label on V1 or V2 or indeed any of these areas is not quite the right way of framing the question, that we should actually be thinking about what the neural processing for particular functions actually is, rather than trying to say V1 does this for everything.
Cool. Fantastic. On to David Heeger.
Yeah, I guess I wanted to answer directly Ruth's question and then follow up also with, but just by doubling down on what Andrew just said. There are clear differences in the effects of normalization between central and peripheral vision. The idea of normalization, the reason I called it normalization is because it's analogous to normalizing the length of a vector, right? You have a vector of unnormalized responses, you halfway rectify and square each of them, you divide by the sum of the squares of the whole kind of normalization pool. But in fact, and even in the original description of this, it's not just a flat sum across of the squares, it's a weighted sum. And those weights, the weights in the normalization weights in the denominator vary from one neuron to the next, and also vary systematically with eccentricity. And this has been shown psychophysically as well as neurophysiologically. So the idea of the attention model, the normalization model of attention, well, all of the experiments that have been done to test those ideas are in peripheral vision, right, where the normalization tends to be stronger, in fact. So it's the normalization itself is eccentricity dependent, I'm not sure that the attentional gains are necessarily systematically dependent on eccentricity. The other thing I wanted to say, doubling down on what Andrew said, is at least from my own goal, my own perspective, is I want to do away with loosely defined terms like attention and cognitive map, and replace it with, formal math, systems of equations, right? So attention becomes a gain control. It's a multiplier in an equation, right? I'm not quite sure what cognitive map means. It can be expressed mathematically, but to me that's the goal, is to end up with a mathematical description, an analytically tractable theory that captures all of the phenomena, fits data, makes predictions. The point is, like other, big theories in science, you get to a point at which you don't need to do any more experiments. You can just use the theory to do calculations and predict what the outcome is, right? I mean, when aeronautical engineers design a new airplane wing, they don't have to test it. They know it's going to work. They put it on a plane and it works, right? You don't have to do more experiments because the principles are so well understood. And that's our goal, I think. In my view, that's our goal.
Good. So we've got Henrika and then Pieter on our list. But I'd also encourage people to ask questions in the audience, right? But Henrika, if you wanted to jump in on that point.
Well, I also just wanted to respond to Ruth, even though it's even though she didn't mention anatomical differences, but I think anatomically we know very well that the feedback certainly to the periphery versus towards the center of gaze, appears to be different, and it appears to be more multisensory towards, for instance, the peripheral representation. So I do think there's room for kind of being meaningful differences in terms of how modulator influences work in V1. And I mean, just sort of back to our study, I think we went out to maybe 14 degrees, so which is oftentimes already referred to as pretty peripheral, but of course we don't know what would happen in the far periphery. And it could be that things might be somewhat more different in the far periphery. So basically just I think seconding this impulse, so I think it's it is very helpful to actually not treat, or I think it's helpful to potentially not be open to the idea that V1 is really not treated as uniformly, but really as differently between kind of center of gaze or representation of center of gaze versus representation of the far periphery in terms of what things are doing.
Sweet. And then I think Pieter had a comment on this.
Yeah. So I would like to say something about cognitive maps and equations, triggered by what David just said. So why a cognitive map? So we were inspired by a finding in which we did a task in which monkeys were looking for an item of a particular color, and then had to trace a dot with that particular color starting at that location where they found this thing. So this first suggests that V1 can be used as sort of a place where you highlight items that are relevant for perception and use it for your next cognitive steps. And this is definitely related to things in the psychology of perception that psychologists call object-based attention. So basically what we find is if you attend something, then all those features of the thing you're attending are labeled with enhanced neural activity. So that is also maybe a function of this cognitive map. Now, about equations. So I love to put a lot of these things in equations, but we also have to realize that we now live in a time where we have these deep neural networks, and the equations tend to get a little bit hairy here and there. So I'm very happy to also be guided by these concepts that are maybe not as mathematical, but definitely guiding our thoughts about how vision works. And that's why I would like to claim that cognitive map and object-based attention might have places in our thinking.
Okay. So Xiaoping wants to follow up on that, and then after that, we're going to move to a question from the audience. Thanks, Xiaoping.
Thank you. Yeah, I'd like to also follow up from Hendrikus and and also Tony. So there, indeed, this looking between central peripheral should really look further, and especially about feedback. It's a falsifier prediction, so therefore, even falsifiable position, even falsifying a point of view, especially my point of view, is highly welcome. And so that's the one thing. Second thing is regarding Tony says there is a quantitative difference in terms of cortical magnification factors. And what I'm proposing is actually a qualitative difference. It's not just quantitative magnification. With feedback, without feedback, with illusion, without illusion. These are qualitative differences. And again, further predictions maybe and falsifiable prediction is one way, one scientific way to actually distinguish between different camps and point of views. And I love the idea of having mathematical equations and models. However, I also agree with Peter's point of view. So sometimes it's actually a number of parameters. Yeah, you say often you will say that the fewer the number of parameters, it's more difficult, more easy to falsify. And also another point of view is one is model, the other is another point of view is functional roles. You can say I have a particular function for V1, whether the V1 is for love, for cognition or for recognition. It's a functional role. Once you have a functional role, you can indeed model it. So therefore, when we should put model together with a functional role, this is perhaps what Peter was trying to say. Okay, what is that in terms of concept? Yeah, that's all for now. Thank you.
Wonderful, wonderful. So I believe we have a question from the audience.
So to be honest, the past couple responses sort of got at my question, but I think it's worth asking anyway. I'm still a little bit unclear as to what the precise disagreement is. I don't really know what a cognitive map is, although I guess the past responses sort of got at that a little bit. I also don't know whether you're on the pro-cognitive map side or it's not a cognitive map side, if there's some set of predictions on which you might disagree. So is it just a matter of talking and emphasis, or is it there's something really different?
It's a fair question. So do we disagree? And if so, what, how are we going to test it? Who wants to go first? Tony.
Well, I hope we can all agree that it's a map, just to get started, right? Since I think that's been established for 75 or 80 years. I share David's confusion and perhaps the questioner from the audience's confusion about exactly what it means to say that V1 is a cognitive map. And I guess I would like to hear Peter or maybe our moderator or maybe Xiaoping tell us a bit more about what distinguishes a cognitive map from a map.
Sure. Peter, do you want to come in or?
Sure. So I was trying to get there a little bit. So in some cases, you need to do something that is really cognitive. So in my case, I've studied a lot tracing a line, tracing a very tiny line among other lines, right? So basically what we find, and psychophysics finds that when you're doing that, you're basically putting your attention and you're painting it over the line. So the line gets labeled with enhanced neural activity. Now that is what I mean with V1 helping cognition. And I'd like then in these cases to think of V1 as a cognitive map, a map where those things that matter to your cognition are highlighted with enhanced activity. That's useful because other areas can then read out in V1 which aspects are now also highlighted. So if you're following this line, maybe at the end of the line there is something interesting, a color or something else, and you want to report it. So then it's very useful to have a low-level representation with all its details and be able to kind of highlight those items that are going to be relevant to your behavior. So that is my personal interpretation of the cognitive map. Another example, and I already mentioned this, is object-based attention. So imagine that you're looking into a box with a lot of toys, okay? And you want to grab one of these toys, but there are so many edges. How are you going to find out which of these edges belong to one toy and which edges belong to different toys? So in this situation, it's very useful to have low-level features, so the precise edges and their depth, because you're going to put in your hand and you want to have your fingers on edges of the same object and not on of two different objects. So that's another example of what I would like to call a cognitive map.
I think Lars and then Andrew.
Yes, I think there's sometimes a bit of a confirmation bias. The community believes to know exactly what V1 does. It's known as one of the best understood area, and there's a bit of Hubel and Wiesel and David legacy in explaining what V1 does. And in logic, there's this challenge. If you want to prove that, you would need to come up with a falsification instead of continuing to confirm it. So, you know, we struggle with our experiments because sometimes the reviewers or the audience says, well, we know what V1 does. Presenting auditory stimulus and blindfolding makes no sense because we know that that's not a feature V1 should be processing, and so it can only be visual imagery or something. And actually in the first paper we had a series of experiments showing in addition that it is not visual imagery. As a field, it's important to open for challenges, even, and that's my starting point, I mean, I fundamentally believe that visual cortex is only processing visual in a proper hierarchy, starting with contours and more complex stimuli and so on. But in, you know, believing that is not sufficient. You need to challenge that. And while challenging, we found principles that, you know, there's additional information. And so the question is, what is it doing? And is that inspiring for the field? Is that interesting? If you do models of vision, is it interesting to think about knowing that there's audition also processed in visual cortex? How do you combine those features? What is a good auditory feature that is making any sense in the visual, you know, in the visual domain? And these kind of questions. There are, of course, other multisensory crosstalk, like tactile and so on. They're very close by.
Cool. So we've got a few minutes left. So we're just going to go to Andrew, and then David, and then Henrika, and then that should be towards the end of the session. So we're going to leave on a high point, I'm sure.
Well, I agree very much with what Lars said, which is that we do actually need specific experiments that challenge the existing model. That's the whole point. And I think that with the V1 experiments that we did with the windowed sinusoid patches, we were looking for something more akin to a perceptual response than we actually found. I think that what the outcome tells us, though, is that with this model that Peter Rolfsummer mentioned about reaching into a box to find a particular thing, actually the V1 representation doesn't help that much. It needs sorting out in various ways to make location a real thing. Location is not actually, there is a map in V1, and therefore we're inclined to say, well, okay, we've got location, but the map actually also contains lots of information about how the two eyes join together to make binocular signals. And until those are sorted out, you haven't really got a map that supports even the most primitive point-to-point of a finger to a particular location.
Cool. So on to David.
Yeah, a couple things. First of all, Peter, no disagreement here. Sure, attentional effects boost the responses of V1 neurons, which then make the downstream processing easier, right? I love an old paper from John Palmer about attention and decision integration theory that basically posits that you know, the way that I think about it is that the neurons somewhere up in the front part of the brain are no smarter than the stupid little receptive field neurons in V1. So how do we make their job easier when faced with a complex, let's say perceptual decision-making task? Well, you make their job easier by making most of the neural signals irrelevant. And you can do that simply by boosting the ones that are relevant and basing the decision on the inputs that are the largest. Then you don't even need to know where they come from, right? But that's all in the form of kind of attentional effects, right? And we can think of those attentional effects as being endogenous attention, in which there's a working memory representation, either in prefrontal cortex or parietal cortex, that boosts the activity of the neurons in sensory cortex, whether that's in V1 or V4 through a similar computation, or exogenous attention, in which there's some particularly salient stimulus, as Xiaoping Li has described and has been modeling for decades, right? If that's all it takes for it to be a cognitive map, meaning that it is a map, a sensory representation which is modulated by cognitive task-relevant factors, I'm all in. The only other comment I want to make is, in terms of falsification, this is why I personally am still on board with the idea of constructing an analytically tractable theory, like classic theories in science. Now, I hear you that we're in a new world with machine learning and deep nets and all that, but I would argue we can have our cake and eat it too, right? So the organics theory, which is an analytical tractable theory of not just sensory cortex, but also motor cortex and working memory, and we're applying it to modeling head direction cells and a bunch of other things as well, is both. It's an analytically tractable theory, and you can swap it in and replace it for LSTMs and GRUs, gated recurrent units, right? And build machine learning applications with it. But what you get along for the ride is now an analytically tractable theory of recurrent neural nets, deep nets built with recurrent neural net architectures, right? And that's a win.
Cool, wonderful. And now for the final word from Henrika.
Oh gosh. Well, I just wanted to follow up or respond to your question, sort of how do we test it, or sort of moving forward, what experiments. And I think I wanted to pick up a point that Paolo made, is in terms of that we don't need new models, but we might actually need new data sets. And the one data sets I think that would be really valuable would be some data sets with a standard cognitive task, where people have documented these cognitive map effects with high precision, high resolution eye tracking, and then really having, being able to really infer the precise retinal input at the resolution, spatial resolution of V1 receptive fields and and so forth. And then just see how far can we actually get by knowing the exact retinal input in such a cognitive task. And I think that would be very valuable and would at least get me to somewhere. If there are convincing non-explainable sort of feed-forward effects and sort of this more general arousal or state modulation and potentially spatial modulation. If there are effects beyond that, I think that I would find compelling. But so far, I find the more complex the task, the more complex the stimulus, and the harder it is to infer the retinal input. And so that's where, for me at least, the confound comes in. And I think moving forward, that would be very helpful.
Cool, wonderful. Well, that's a wonderful note in which to end. So all I want to say is thanks ever so much to all our speakers, both in person and in line. And if we could give them a round of applause, and thanks to you too.
And maybe, sorry, I should, of course, the point that also Toby emphasized as well. I'm sorry, I didn't do back to you again.
Organization, thank you.